discuss, let me first discuss the solution to more than a single element, a single equation. So normally you have many, many more elements, and the final product of the Galerkin or its method, or for that matter, finite element method, would be a set, a large number of linear algebraic equations. So obviously, solving this equation is not a simple matter, as I said. Even today, there's still open issues about that. And among many different methods, the one that I like the best is definitely Gauss elimination method, because it has a certain number of features that we're going to be discussed right now. So what does the method would try to do? Well, the Gauss method would basically first take a stiffness matrix and decompose this matrix into so-called triangular decomposition as the product of a lower triangular matrix that we call L and upper triangular matrix that we call U, like lower and upper. So in L, you have all the components which are on the main diagonal. These are unit values, and then below the main diagonal. And everything which is above is equal to 0. On U, it's the other way around. Everything which is below is equal to 0, and on the main diagonal and above, these are non-zero components. So once you have achieved this triangular decomposition, the solution is very easy. It consists in two steps. One is a forward reduction, the second one is back substitution. What that means is the following. Here we have LU times little u, which are unknowns, so equal to F external. So intermediate value, you call this big U times little u equal to Y, which is unknown value. And then you solve the system L little y equal to F. This system is very easy to solve because you can look into the structural matrix L, and you see that in the first equation, you only have one unknown and gives you directly the value of this y1. And then you take this value, you plug into the second equation, you're going to have one unknown again, and all the way to the end. So going from one equation to the next one in the forward reduction manner, from top to the bottom, you always have only one equation at a time. Then once you know why, then you look into the system equation, which means u uppercase times unknown u equal to y, which is now computed. Now you start from bottom. In the last equation, you have only one unknown, which is un. And then you go to the n minus first, you have un minus 1, which is the only unknown, and all the way to the first, we have u1. So this is so-called back substitution. So these two phases together, they achieve the whole solution of the system. So what is the advantage of Gauss elimination method? First of all, you know what is the number of operations. The triangular decomposition of the matrix K into this L and U is the most costly operation. So it's of the order of 2 times n to the power 3 divided by 3. So if you have 1,000 equations, you have 1,000 to the power 3, you have a billion operations. And it certainly is much more costly than the other subsequent phases, which are forward reduction and back substitution, which are only of the order of 1 million operations. You can also save some computation, given that the stiffness matrix is often symmetric. So this way you can reduce from 2 times n to the power 3 divided by 3 to only 1 times n to the power 3 divided by 3, because U can be written as a, let's say, a product between B and L transpose, where B is a diagonal matrix. There's also a very important issue how to reduce the computation further. If you take a solution in a way that the stiffness is not a full matrix, but is something called skyline, that is, you store only the values that are close to the main diagonal, which are non-zero, only those values will be affected. So basically, this solution is reducing number of operations further, and so you can have it, for example, reduced to as much as the sum of the square of these lengths of every column in this perspective. This is only a detail. I'm going to discuss this further. And the last and final point, with the Gauss elimination, you can very easily obtain condition number from the values of these diagonal matrix D. Condition number happens to be indicator, which tells you what will be the sensitivity of the result for different values of computation. Condition number is basically the maximum eigenvalue of the stiffness matrix divided by the minimum eigenvalue of the stiffness matrix. And if the condition number happens to be large, that means there's a large sensitivity of the computation of your results as you go along. So basically, the idea is really that what you call it, the value of this condition number is something that is really modifying the precision of the results. You can see that the condition number could be very large for the structures like shells, because the stiffness that goes into bending is much smaller than stiffness that goes into membrane. Also, for the cases of fracture or plasticity, the stiffness goes to the plastic modes or fracture modes is much smaller than the stiffness that goes. So all those problems which are complicated to compute, that is the problems with shell structures, the problems with the fracture, they are all very sensitive to condition number. But at least the advantage of a Gauss method is that we can compute this condition number as we go along. Now, if you have a linear set of equation, Gauss method will gives you everything. So you can very easily in these 3 steps compute solution directly. So you know what is the number of operation, what is the cost, what's condition number, and everything. Now, if you have a set of nonlinear equations, when that happens is when the behavior of the bar is nonlinear elasticity or plasticity or any of these type of things. The idea that I want to start with in this case would be idea of incremental analysis. Now, solving this problem, you can introduce so-called pseudo-time parameter T, which is a simply convenient parameterization of our external loading. In other words, what we are now trying to achieve with incremental analysis is the idea that you do not apply the whole loading in one step, but you imply this in terms of a sequence of increments, and you assume that in each and every increment, the real nonlinear behavior could be approximated by the corresponding linear behavior. And then you can solve this by using the Gauss method of elimination, like we just explained. So that's really the basic step of the incremental analysis. How is that achieved? Well, you simply say if the total load applies up to uppercase T, let's say from 1 to 10, then I can define this in 10 steps and increase it from 0 to 1, from 1 to 2, 2 to 3, and so on and so forth in 10 steps to reach my 10. And I'm going to focus only what to do in a particular increment. So basically what to do in particular increment, if I have loading, I can typically, for many cases, write this loading as a fixed pattern, F0, multiplied by some kind of G of T, which is a time variation of this loading. The easiest time variation is simply to say G of T is equal to T. So if you go from 1 to 10, initially T equal to 0, load is 0. When T is equal to 1, well, G is equal to 1, and all the way to 10. And multiply 0 by 10, and you have a final loading. So incremental analysis for external load is very easy to achieve. You simply keep your F0, multiply by G of Tn plus 1 minus G of Tn. And this is the increment of the external load. Now, how do I get the increment of the internal load? Well, the idea here is that I have to define so-called tangent stiffness matrix, which will be multiplied by the incremental displacement. And that's the goal of the next step. What's incremental displacement? This is displacement that takes me from displacement time Tn to displacement time Tn plus 1. Again, this example, if uppercase T is 10, and I have 10 steps, so in the beginning, D0 is equal to 0, U1 is incremental displacement taking me from 0 to 1. When I add these two, I'm going to get displacement at 1. Then I have another incremental displacement at time taking me from 1 to 2. I take a previous value at time T1. I add this incremental displacement. I go to displacement D2 and so on and so forth. So the main idea how to get this tangent stiffness, and this is obtained by so-called consistent linearization. What that means is basically if you look into what Taylor formula applies for any function g of x, respect to x, it goes as follows. Imagine this is your nonlinear function. It could represent a particular nonlinear response of my, let's say, trust bar when I have only significant degree of freedom. So when the displacement increases, I have a nonlinear response, but I want to approximate this with a particular linear response. So I simply take a Taylor formula and I truncate after the second term. In other words, if I want to obtain linear approximation of the function value at x plus u, I take a value at x, well, here it's called x bar because that's its chosen value, plus the first derivative of that function with respect to x, computed at x bar, times the increment u. So basically, here, instead of traveling by this nonlinear thick line, I'm traveling by this linear form, which has a function value plus the first derivative times the increment, and that's the only thing that I need. Now, of course, this is not for the scalar function of x, with the u being increment, and basically what we needed for the scalar function of vector. So here's interpretation with x being a three-dimensional vector. that could be computed as a Gato derivative with respect to some kind of parameter t that is parameterizing how this increase can happen from x bar to x bar plus tu. And so then you can say that this is like a computation on my Gato derivative. Basically, what I need is not a three-dimensional space, but I need n-dimensional space where n is the number of unknown displacement vectors. And my function is the weak form. It's the product of the nodal values of virtual displacement times the residual, the difference between internal forces and external forces. So then I do linearization in terms of the incremental displacement u n plus 1, given that I have the values at Tn. These are displacement at Dn, and I can find that basically the tangent stiffness can be obtained like the normal stiffness. In other words, I have still the shape function derivative of NA and NB for the real displacement and virtual displacement, but multiplied by the current value of the tangent elastic modulus as opposed to the Young's modulus. So in the very first step, when t equal to 0, this will be just like a linear elastic stiffness, and then every other step, given the displacement gets bigger, the tangent modulus is typically different than the initial elastic modulus. And so this is the way you go from one case to another. Now, this tangent stiffness is, according to Taylor's formula, is the best approximation of the true nonlinear variation of the function. Basically, I have that f at dn plus 1 minus f of dn related to k at dn, tangent stiffness and time tn, times the incremental space n plus 1. Goes to 0 quadratically, so it goes much faster than the increment of un plus 1. And that's the only matrix which has such a nice approximation problem. So, okay, what does then incremental analysis would achieve? You linearize internal forces. That comes down to saying this is the value of the internal force at time Tn, plus the tangent stiffness at time Tn times incremental displacement of un plus 1, equal to external force will be at time Tn plus the incremental displacement at n plus 1. And then you assume that at time Tn, you have achieved your equilibrium. In other words, the internal force and external force at time Tn were approximately the same. So you can cancel these two. And then from the equation above, taking into account this cancellation, you simply obtain tangent stiffness computed at time Dn plus 1 times incremental displacement un plus 1 equal to the incremental force, the delta f n plus 1 external. But this equation here is exactly the same as the equation that I was solving here for the linear analysis when I say I want to solve k u equal to f. The only difference for linear analysis, stiffness was only one stiffness, u was the total displacement, and f external was the total force that I applied. And then I apply, of course, Gauss method using all these steps that I just explained. So now in the incremental analysis, I take the same steps, only applied independently for each and every increment. In other words, for every increment, I now have to factorize in terms of these two triangular U and L components for tangent stiffness and time Tn. Then I have to compute my incremental displacement. And once I computed it for the incremental force, of course, once I computed it, I add this value at the previous displacement and I carry on to the next time. And then I simply go increment by increment and then I achieve the final result. What would that result look like? Well, this is my true nonlinear response. And this is like increment by increment linearized response that I'm computing. So obviously, this linearized response and the true nonlinear response are not the same thing. I just have an approximation of what really is needed. However, on the other hand, you can make these steps very small so that this quality of this approximation gets better and better. And so if you don't like the fact that at every increment you have so-called residual, in other words, the difference between external load and internal load for the particular area of displacement is not zero, because incremental analysis doesn't do anything about this residual. It simply keeps accumulating the residual as it grinds along. You basically have now to stop and try to iterate in order to get rid of this residual. So the way it works, it goes as follows. You can say, okay, I'm not happy by the fact that linearized version of my equation did not give me residual equal to 0. So the way it works, okay, I'm going to take this residual, which is difference between the external load, which I really have, and the internal load, which is computed for the value of the displacement dn plus 1, which is provided by the incremental analysis, which is nothing else but the value of the time Tn, dn, plus incremental displacement un plus 1. And so happens this residual not being 0, I'm going to treat it now as an extra incremental force that could be feeding the second iterative improvement on my incremental displacement. So I have to form my tangent stiffness again at the value of this displacement which was provided by the incremental analysis, which is dn plus un plus 1. And I have to provide this residual. Solving this, I get my second iterative improvement to displacement. And so I get a better estimate of what this displacement should be. This is blown here for the step 3n. See, this was incremental analysis, and this is just one step going from n to n plus 1. So incremental analysis, first step was here. This was my residual that was feeding the second iterative correction. So here I do tangent again, and I get my second iterative correction. You can see the displacement now is much better in the sense that residual from the first iteration, residual from the second iteration, definitely are not the same. If I'm not happy with this value of residual, I still carry on. And from one iteration to another, I can make a residual as small as I possibly wish. So here's the summary of this incremental analysis combined with Newton method. That was this iteration that I just explained. Namely, in the first iteration, you take the value of the displacement that you computed at time Tn. Then you compute the subsequent iterative improvement of your incremental displacement by using the residual that you computed from the previous iteration. You update the displacement. They say that the total displacement at iteration I plus 1 is the displacement at iteration I plus the iterative improvement of this incremental displacement. And then you compare this against the tolerance to see whether this is kind of small enough in this particular setting, and you carry on. So the question of the tolerance goes as follows. Either you can compare the increment in terms of, let's say, residual force. This is the most usual computation. However, sometimes the residual force gets to very small values. This is typically the case when you're computing the limit load. In other words, when the response becomes almost horizontal. This is typical of plasticity problems and so on and so forth. So in this case, what you can do, you can check what is the iterative contribution to incremental displacement, and you can ask that this one be smaller than particular tolerance. But then you can have something like rubber where this goes very steep up. So iterative contribution of incremental displacement could be small, but the residual in the force could be big. Hence, if you want to have the best solution for both, what you can do is the tolerance to be chosen when to stop iteration by using increment of the iterative displacement and increment of your residual, and compare this against certain tolerance and basically decide what you want to do. So what's really good about Newton's method, first of all, is that once you're close to the solution, you can have so-called quadratic convergence rate. In other words, it is very easy to show that basically that these things are once you get close to zero, that the number of zeros behind decimal point is doubling. In other words, these are typical computations I've done for one of these problems. These are the values of the residual. So as you go along, of course, when it gets very small, these are subsequent iterations. Here, 1, 0, then you have 2, then you have 4, next one will be 8, and so on and so forth. So this really is a illustration that Newton method of iterative improvement of the incremental analysis converges very fast. And so basically, if you really want to have a kind of acceptable solution, there's no reason to stop with only a few iterations. You basically can have a number of iterations as large as you want, and to really drive down the residual to very, very small values as you go along. So this is really the kind of solution procedure for the linear analysis and nonlinear. So I explained to you Gauss method, and I explained to you incremental method with Newton improvement. Now, the second part of this technology, the finite element method, would be basically going into so-called isoparametric element interpolations. And that's what I wanted to explain. So imagine now that you have let's say, to construct the solution method by using a number of these truss bar elements. And for some reason, you decide that not all of them are the same because you want to adjust your approximation in a better way to particular loading, which might have a steep gradient somewhere and then maybe not much going on somewhere else. So the idea would be here now to try to make the work uniform, not to worry about that each and every of these elements has a different position and different orientation or whatever it is, but to kind of unify this and turn it into sort of factory massive production. how do we do that? Well, the idea is like with the two things that we have to do. One is that basically is what you call it. We switch from the physical domain to so-called isoparametric domain, which is the first thing here. And then second thing is that we introduced so-called natural coordinates, so that in this domain, every element looks the same. So that's precisely what is going on in each and every computer software. And this is what I wanted to explain a little bit more in detail. So if you really want to use all the details of the results that are provided, or even more importantly, if you want to change something and adapt to your own particular use of these computer codes, then you know how to do that. So these are the key things that I actually just mentioned. So if you really want to make every of these elements that are here, element 1, 2, 3, all the elements look the same, you have to do the change of coordinate. In other words, you first split the total domain omega into number of these elements. Omega E is a typical domain of a particular element. It goes normally from x, let's say A to xa plus 1, if it's a particular element E. So at every element E, you're changing these values of x, simply because elements are not positioned in the same manner. But if you want to compute them in the same way, then you say, okay, I transfer my coordinate x, I replace it by so-called natural coordinate psi, and that one goes always from -1 to +1. You'll see that is really imposed by so-called numerical integration type of point. So basically, the idea here is that with this type of value, I'm now able to compute, to do this computation for each and every element in a very much unified manner. And this is like a series production. So instead of worrying how to produce each and every element in a very special way, with very special coordinates, very special shape function, and so on and so forth, I'm actually saying that all the truss bar elements which have only two nodes, no matter where they are placed in the real structure, could be treated in exactly the same manner by using this natural coordinate transformation, which allows me to really simplify this, let's say, computation and make it kind of very efficient because I keep turning this into the same part of code. Typically, it's called subroutine or whatever function, so to prepare this for typical. So when you talk about finite element jargon, you're typically talking about the library of finite elements. In other words, you're choosing a certain shape functions for representing your solution, either like truss bar or beam or shell or solid, and so on and so forth. And that means a particular execution behind what this finite element software is doing. So let's look into these details for two node truss bar elements. The point is the following. Basically, I have a description which is done at the global level, where I always take into account where exactly this element is placed, what exactly are its nodes, what exactly are degrees of freedom. So every time I use a global coordinate x, which is chosen for the whole domain of this element, it goes from 0 to L. On the other hand, I can do local or element description where I focus only upon a particular element. In order to be able to deal with this element in a unified manner, I'm replacing the true physical coordinate x by so-called isoparametric coordinate psi, where the value of these coordinates at the end of interval are going from -1 to +1. The choice of -1 and +1 is conditioned by the choice of the numerical integration that I'm going to be using in order to compute these results as we go along. So here is basically, I said the domain that is in the real element going from in the real coordinates from xa to xa plus 1. In my local description or element description, it goes from xi1 and xi2. As I said, typically xi1 is -1 and xi2 is equal to +1. Then here, denoted the nodes. Here, I take the nodes to be a and a plus 1 that goes from 1 to number of nodal points. So you have nodes 1, 2, 3, whatever to 10,000. But here, the nodes, when I have local descriptions, are always 1 and 2, because you have only element with two nodes. So I don't care giving any other number but 2. So degrees of freedom, these are nodal values of displacement at the nodes A. They're called dA and dA plus 1. So it could have been, if it's 1 to 10,000, it could be 1 is 57, the other one's 58, or whatever it is. It could be whatever 9,999, the other one would be 10,000, just if it's in the end. But here they're always 1 and 2. Again, because they're two node truss by element, I only have 2 degrees of freedom. Now, shape functions, these are linear shape functions in X. For typical element, when you had only one, it's 1 minus x over L. The second one is x over L. Here, you're going to express them in terms of natural coordinate xi, and we see how you do that. Hence, the interpolation for this element would be NA of x times dA plus NA plus 1 at x times dA plus 1, whereas here it would be N1e of xi times d1e plus N2e of xi times d2. So you see, here you have information which is always global, whereas here you only have information which is now local. So basically, how do you switch from local to global? How do you replace the polynomial x with the polynomial xi? Well, first of all, we had a linear shape function in x, so we're going to have a linear function in xi. Hence, the transformation that takes us from x space to xi space has to be so-called affine transformation, which is equal to a constant c1 plus c2 times xi. And this is going to give us x of xi. In order to match these two, we want to have the end of the intervals match each other. So what are the end of the intervals? Well, here they are xa and xa plus 1, and here they are xi1 and xi2. Xi1 being minus 1, xi2 being plus 1. Hence, I can say that x of minus 1 has to be equal to xa, and x of plus 1 has to be equal to xa plus 1. So if I take these two conditions and I take this equation here, I can write that this will be like a C1 minus C2 equal to XA, and here would be C1 plus C2 equal to XA plus 1. So from these two conditions, I can very easily obtain that C1 should be equal to XA plus 1 divided by 2. In other words, C1 should be like the middle of this interval of this real element, and C2 should be equal to XA plus 1 minus XA divided by 2. XA plus 1 minus XA is nothing but the length, the real length of this element, which is equal to LE divided by 2. When you have a transformation of this kind, often you can compute so-called the Jacobian of such an affine transformation. This is simply derivative of x with respect to xi. And it so happens with C1 and C2 being constants, which are expressed here, this is simply equal to LEO2. What is Jacobian? Jacobian is the measure how we obtain the distance in particular space. So in the real element space, the distance is from xa to xa plus 1, indeed is equal to LE. This is the true length of this element. Whereas in the isoperimetric element space, distance goes from minus 1 to plus 1, which is equal to 2. So this is the ratio of distance of the real element versus the ratio of distance of its isoperimetric representation. And that's actually what this Jacobian does. So for the simple case of two-node truss-bar element, the Jacobian is constant and basically gives us really how we measure these type of distances. Now, we obtain simplicity that we can obtain each and every of these elements represented as the same domain. But the complexity now is to obtain these shape functions. So what do? We have how x is defined as a function of xi. We have previously defined NA of x, and now we use x as a function of xi. It turns out that we can this way express what is NA of this element in the space of xi. And so it could be very easily verified that this is simply 1/2 1 either plus xi for the node a equal to 2, or 1 minus xi divided by 2 for the node a equal to 1. Note that these shape functions, the way they are used to construct geometry, this is now another way of writing, because here I had the x to be c1 plus c2 times xi, where c1 is xa plus 1 divided by 2, and c2 is le divided by 2. This can also be written as a n1e of xi times x1e plus n2e of xi times x2e, where n1 and n2 are nothing but xa and xa plus 1. I mean, in terms of numerical values. Now, you take the same shape functions and you construct displacement interpolation by using these shape functions. So that becomes NA of xi times dA. So the shape functions are the same. The only difference here, these are like nodal values of coordinates of the true element, and here these are the nodal values of the displacement of your true element. So if we make this choice, we are talking about isoperimetric elements. They employ the same interpolation functions for the, let's say, real displacement field. And of course, you can do the same type of interpolation for the virtual displacement field. Now, if we have expressed the displacement field as a function of xi, natural coordinate, we can still not change what is the interpretation of the deformation. Deformation is the derivative of the real displacement field with respect to the coordinate x. So how do we obtain now, given that everything is functional psi? Well, it's simple enough. We can use the chain rule. In other words, we need this dA of psi, which is nothing but derivative of shape function with respect to x, times the nodal displacement. But given that this shape function is functional psi, we can do this to be derivative of psi times d psi dx, which is written as 1 over dx d psi. And now dx d psi is nothing but Jacobian of our interpolation, which is written here. So I go back here, I take this Jacobian, which is 2 over L. And basically, by getting this derivative NA with respect to psi, given that this is always 1 plus minus psi, so this is even always like a plus 1/2 or minus 1/2, or you can write it as a minus 1 to the power A being 1 or 2, and then 2 over L and 1/2 cancel, and you at the end you have this minus 1 over A divided by L times B. So in other words, the strain is still the displacement at one end. This is a displacement 2 minus displacement at the other end, which is displacement 1 divided by L, which is precisely the definition of the strain. Hence, we did not really change the final result. We have just changed it with something that looks more complicated. Well, it looks more complicated to human who is used to making this little computation by hand. But to a machine, it looks much more simpler because this way you have broken the computation of the strain field into a number of subsequent steps where each and every one is very simple and it can be reproduced in a very quick way, just grind it one after another. So this way, you can obtain the strain field as a function as a parametric coordinates and without any problem. Now, the next step is computing these internal forces. So if you go, for example, to internal force of a two-node transbar element, that means you have computed your strain field. Now you can put it into the expression for the stress. Of course, you multiply this by your virtual strain. So again, you need another this operator B. And so when you express all this, it turns out that this is nothing but integrating without this constant. So it has to be either minus or plus 1 times the sigma being the stress in the middle of this bar. If you go to the tangent stiffness, well, here you have a expression for tangent stiffness. Recall, this is like a linear expression when you have just Young's modulus E instead of the C. Now, in no linear analysis, you have to compute the current value of strain, which you do by using this product of the B operator, which is dn C dx, times the nodal value. So this gives you current value of strain for the strain to the tangent modulus. And then you basically multiply this by either BA and BB, and hence you obtain this to be your tangent stiffness. Another one that becomes like C over L. C over L being your what you call it, the tangent modulus, and then you have a minus 1 plus 1 minus 1 plus 1. This is the standard form of a tangent stiffness of your matrix. Now, the fact that we switched from the physical coordinates to the natural coordinates cost us a certain, let's say, effort. In other words, we have to do some conditions which guarantee that our transformation from one coordinate to another makes sense. And these are so-called the consistency or at the end convergence condition for the finite element approximation. First of all, we ask that these shape functions that are function of psi be sufficiently smooth so that the first derivative computation be unique expression. That's actually what it means when you say that NA should be function C1, because that means when you take a derivative, the expression still continues all over this domain omega E. This is not what we ask for the whole domain omega, which contains all these elements. We can afford that from one element to another, we can handle the shape function derivative discontinuities. Simply the finite element method has this advantage in this respect. And the final condition is the sum of all the shape function or particular element has to be equal to 1. Now, why are these conditions imposed? Well, first of all, the first one is a practical requirement, because in computing the tangent stiffness, if you go back, you know, you have these derivative of the shape functions NA, derivative of shape functions NB. So if you have a component 1, 1, that means you have a derivative of shape function squared. So basically, you want every derivative to be smooth enough. So when you're computing integral over omega e, which is a domain of integration of a particular element, you want to have a single expression to handle. Now, if you go from one element to another, you can have this discontinuity, but the worst case scenario, you cannot have let's say Dirac square. That's basically the problem here. If you have a continuity, let's say of these shape functions, then you can avoid the risk that basically you have like a Dirac function. If you're not familiar, this is the function that takes a particular value. It's like a distribution function. So if you have any function f of x and Dirac at x minus xc, that takes the function at xc. So basically, this is the kind of thing that is also needed. And the final one, that the sum of all these shape functions is equal to 1. Basically, this is the case when you have a displacement interpolation such that NA of psi times dA is basically equal to if all displacements are equal, that means that's some kind of value equal to C0. This is just the motion of the rigid body. Then you want this displacement also to be the same motion of the rigid body. Hence, you simply ask that the sum of all these shape functions be equal to 1. So this is the type of computation that goes into interpolation of displacements and strains and stress. Now, if you have an infinite element technology, computer software, you also need to represent the loading. So this is not really a crucial requirement. This is more like a convenient requirement. But for many codes, the external loading is also represented by using the same shape functions as those that you have using displacement. There's really nothing fundamental there, except for convenience, because these are shape functions which are already available. So why not use them to obtain the corresponding external load? So here you do that with the external load for 2-node truss bar element, and you obtain corresponding values of the loading, where you have this load to be distributed this way, NB times B, where NB are shape functions. And then, of course, there has to be multiplied by the virtual displacement, the corresponding shape functions in NA. Hence, you can compute for 2-node truss bar element, the consistent interpolation of the loading would be something like that. If the B1 and B2 are the nodal values of a distributed load, then the corresponding equivalent load would be equal to LE over 6, L being the length of the element. B1 will be the value of the load at the left hand, B2 will be the value of the load at the right hand, and here you have B1 plus 2B2. Please note when these two are the same, in other words, you have uniform loading, like that simple example, when B1 and B2 are the same, this will be 2 times B plus B, this is 3B, this is also B plus 2B, that's 3B, 3 divided by 6, this is 2, so that becomes B LE divided by 2. So you get logical expression that external load is a total load, B times L, divided by 2 for each node. Okay, now, if you are not happy with the truss bar, which has only 2 nodes, then you can switch to a truss bar which has 3 nodes. So basically, what we do there is we obtain high order representation of the geometry. In other words, what we do is we take let's say if I should I go back to imagine now this was the whole structure. So here you have like n nodes, and you have like if we took 2-node element, there was like n minus 1 number of elements. But these elements could have been like with 3 nodes. It could have been 4 nodes. What happens if you do that? Of course, you have smaller number of elements, the same number of nodes, but you will have higher order polynomial approximation for each and every of those elements. So this is the goal now to see how we can achieve that. Higher order polynomial approximation will provide better accuracy of representation of displacement field, its gradients, and so on and so forth. So let us look into how we deal with that. So it's no longer linear transformation from x to xi, but it will be quadratic and cubic and so on and so forth. So here's the way it goes. Imagine now we want to have NEN nodes, where NEN should be bigger than 2. Our parent element still goes in terms of natural coordinates, so -1 to +1. only now instead of 2 nodes, we have n nodes. So the question is, how do we construct shape functions? By definition, each shape function should have a value if it's NA. It should have value which is equal to 1 for xi equal to xi A, and 0 and all the other values of xi for other nodes. The easiest way to construct this is in terms of so-called Lagrange polynomials. Lagrange polynomials are written here in terms of these monomial terms as the product, or explicitly given here. What exactly do you use? Well, basically, you take here a monomial which is xi minus xi b, where b takes all the nodal values except for b equal to a. And you divide the denominator, you put ca minus xi b. So basically, this way you're sure when xi is equal to xi a, these two will be equal to 1. And when xi is equal to any other value that is xi b, this will be equal to 0. This is written explicitly. So you can see what actually happens. The only value which you're missing in the table is the xi minus xi a. And this will be, when you replace this xi by xi a, this will exactly match what you have in the denominator. So the value of the shape function will be 1. On the other hand, if any other value is taken but a, this one of these monomials will cancel and you have value equal to 0. Let's see this abstract general expression illustrated for 3-node truss-bar element. Here is a parent element. It goes from -1 to +1. So the nodes are xi1 equal to -1, xi2 equal to 0, and xi3 equal to +1. The real element also has 3 nodes. They are not necessarily nicely centered. You can be now shifting them back and forth. The only point I'm trying to make immediately, you cannot be shifting them too much because you're going to be distorting approximation of this true element, and you have so-called distorted element. Jacobian will no longer be positive, and you have one of these variational crimes where it can no longer be used to obtain the corresponding solution. So what does it actually provide? First, you have a shape function that look like this. So these are Lagrange polynomials. Say they're constructed precisely this way. And let me try to work it out. So basically here you have like a, for n1, you will have a, go back here, sorry. Go back here, you have a xi minus 1, so this is xi plus 1. And then the second one, sorry, will be xi minus 0, and the second one will be xi minus 1. And that's precisely what you get here. Divided by -1, minus 0, then -1, this is 2. So this becomes 1/2 xi minus times xi minus 1. In other words, when xi is equal to -1, this becomes -1, minus 2 times -1 is +2, divided by 2 is 1. So this value here is 1. For xi equal to 0, this one cancels, so this is equal to 0. And for xi equal to 1, this one cancels, so this is equal to 0. The same goes for this guy, only this is on the other side. So this is 1/2 xi times xi plus 1. And then finally, the one is a bubble function. When for 2, you basically have -1 and +1. So 1 plus xi divided by 1 minus xi, it could be written as 1 minus xi squared. So this is equal to 0 when xi is either plus or -1, and it's equal to 1 when xi is equal to 0. So this is kind of nice representation of such an element where you already increased the accuracy because now your shape functions are quadratic. Of course, you need 3 nodes, but you will see there's some advantages that basically can go into the construction of such element. Now, Jacobian of such transformation, because now x is n1 of e times x1 plus n2 of e times x2 plus n3 of e times x3. So this is 3, should be a mistake. And then Jacobian should be derivative of these shape functions. Obviously, you can see derivative. The first one is something like xi minus 1/2. The derivative of the second one will be minus 2 xi. And derivative of the third one should be xi plus 1/2. So these are linear polynomials. So basically, the Jacobian is a linear polynomial. That means the way you measure the distance varies linearly along the physical element, and is not constant like it is for 2-node truss-bar element. Now, one should be careful not to have a Jacobian become negative, because this would imply that measuring distance in physical space and measuring distance is isopyramidal space do not respect the same rules. So whatever you want to do, the condition is that Jacobian has to be positive. And given that the values of Jacobian should be defined between xi equal to -1 and xi equal to +1, you compute this Jacobian for 3-node truss bar element, it could be written as a J of C into LE over 2, where LE is the difference between one extreme, x2, minus another extreme, x1. And then basically, this should be x3, sorry. And basically times psi, x1 minus 2 times 2 plus x3 should be positive. So from this expression here, I can obtain that for psi equal to plus 1, it follows that x2 should be smaller than x1 plus x3 divided by 2. This is the center of the element, plus L over 4. And for the other one, it follows that x2 should be larger than, this is the center of the element, minus LV4. I think this is presented here. In other words, if you have isoparametric element, you have a perfect positioning of the nodes. In your true element, for some reason, you might want to move the node which was supposed to be in the center to some other location. In doing so, you are violating the fact that Jacobian is the best place when it's in the center. And okay, it's for you to do it, but in that sense, you cannot do it too much. If you push this beyond L over 4 from the ideal position in the center, the Jacobian becomes negative, and then you really have a problem computing this type of thing. So this is the kind of the approximation that one has to respect, and in the first case of what happens when the element is distorted. In other words, the higher is the element order, you have the more precise, but only under certain ideal conditions. You not necessarily have these wonderful conditions all the time. So basically, you have to really worry about how you actually construct this for the higher order elements, and you worry about element distortion and so on and so forth. So once you have your displacement interpolations, please, do you have a question or something?
Yes.
Yeah, go ahead.
If the Jacobian is none, what does it mean exactly?
If Jacobian is what?
None is equal to 0.
If Jacobian is equal to 0, well, in any case, if I go back for 2-node, the truss bar element, for 2-node truss bar element, as I said, the natural element goes from -1 to +1. So the length of the natural element is -1 to +1 is equal to 2. And the real element goes from xa plus 1 to xa, which is the length of this element, Le. You can see the Jacobian is the length of the real element divided by the length of the natural element. So basically now, if your Jacobian becomes 0, typically that means that you messed up something with your procedure, that basically Jacobian cannot measure correctly the ratio between one and the other. Because here in this higher order approximation, Jacobian is no longer constant, because you shifted. If you move this element, if you move this node in the center, in the physical domain, if x2 is precisely x1 plus x3 divided by 2, what's going to happen? This will cancel, and Jacobian will be again constant. So we will have a perfect quadratic interpolation, not only in x, but also in psi. But if you move this node to any other location, you will start getting a way how you measure the distance in a physical space as opposed to natural coordinate space in a different manner, which will be described as a linear function of psi. And then this is okay. If you like it this way, you want to move this node because you like it there, because some force is applied or any other reason you have it, not to have a perfect sort of structured mesh, but distorted mesh. But the problem is if you move it way beyond this limit, which is L over 4, divided from the center, you're going to turn Jacobian to 0 or worse, negative. In other words, then the way you measure distance in the physical space and the way you measure distance in the natural coordinate space is no longer the same. So you have to have so-called bijection. That means for one and every point, each one point in this physical space, you have the one and one only point in the natural coordinate space. Because don't forget, we did this transformation to natural coordinates because what you wanted to have a faster computation in the way that that basically allowed us to unify computation of all these integrals that lead to tangent stiffness, external load vector, and so on and so forth. So these are kind of things that we needed. But basically, if we have now higher order approximation, we still have this unified domain that goes from -1 to +1, but Jacobian becomes like let's say a non-constant if the mesh is not perfectly respected. So basically, that is something to worry about. As I said, initially people try to compute high order approximation with these elements, but turned out that they have so much sensitivity and they are good to obtain some special solutions. But if you have a very general problem, nowadays people really prefer much more lower order approximation, which are much more robust, and they can avoid all these difficulties. So this is the stuff that I try to really point out what could be the danger. How to distort element too much without knowing it. But in a very complicated problem, in 2D, 3D, you'll see there's even more problems with the high order approximations. And so basically there's really lots of issue and not to push mesh into too much distortion. In fact, there's as I said, the most successful company in France, this Dassault system, which produced CATIA, they started simply with the very modest objective of producing mesh very quickly. And they developed now combining all this software and whatnot into all kinds of things. So it was equally complicated, if not more, to provide some nice finite element mesh for complicated problem than it is to solve the problem, at least in terms of the practical tools. That's why these things are kind of important to tell, to know what the hell, this is the reason and why do you do it now. So imagine now when we compute this high approximation, now displacement is obviously a quadratic field, strain will be linear field, and of course it becomes quite tricky to compute these type of things with the different shape functions, and we'll see this is done by the numerical integration. So in the summary of all these results, here is the results. So you basically have a computation of these internal force to be obtained by using these integrals from -1 to 1, and then you have a tangent stiffness, you have external load vector that you have to obtain. Maybe I would go back and try to find your homework. So this is page 87, what is this? Maybe 34 up, yeah. If I go back to this problem, okay, imagine this is your problem for homework now. And what you can do is you can try to do two following things. You can, let's say, let me define your homeworks. It's not really Blackboard, but what the hell, almost is good. So imagine if you have this element, which has a T bar, which has a little b, and u0 could be 0, so you don't have to worry about that one. So here's a little b. This is your T bar. So can you compute the solution for ups? One. So here you have a oops. So this is this one, this is this one, this is this one, this is this one, and then you put this one. Okay. So let me try to define this. So this is the two elements with two nodes. Okay, this is one element. with three nodes. This is also one element, three nodes, but they are not the same. So this is here L over 2. And this here is L over 4. So we'll see what happens in this one. And then basically you can do that first and using x coordinates, like I explained. And then use isoparametric. Under A, you can use this one. And then you can use that one with isoparametric coordinates. Is that okay? This will be like a homework. You don't have to submit it to me. This is already the second one because I asked you first to check strong form, weak form, and type of thing like that. Yeah. So, and then please comment. You have here exact solution. So comment. Sorry, here. Comment difference in strong form solution and the weak form for solution. Okay. So that should be I think good enough for this homework. I hope you can grab this and you copied all these things, and this will be already nice illustration. In other words, here you compare this. What I mean is super convergence properties. That's it. Okay. So yeah.
Sorry, this is the only homework, or is there another one before?
Yeah, the one which was like showing that the strong form and weak form are equivalent. That was another one that is also useful to see, to go through this process once, because I have just thrown to you weak form and I never really showed that they are the same. So you can go through this integration by parts and stuff like that to get that this is indeed the case, and confirm to yourself that the weak form development was meaningful as the way I did with the strong form. Okay, that's the one. Right. So basically, going back to this one, what we have shown is we have developed for high order interpolation all these different tables. That is the stiffness matrix, what you call it, internal force vector, external force vector, and all this kind of stuff. And you realize that, for example, matrix B is quite nasty because Jacobian, you have to divide by Jacobian, and here obviously you found that Jacobian could be linear functional psi. So now all of a sudden you don't have polynomials anymore, but you have rational functions. And so that becomes quite tricky to compute these things. In fact, you know, in the early day of software development, before this invention that I'm going to present now, which concerns the numerical integration, it was actually quite laborious to provide some kind of stiffness matrices, and people would spend the summer vacation to develop, let's say, a stiffness matrix for complicated shell element and things of this kind. So the invention I wanted to present in the remaining part of today's lecture is basically this story on what you call it, numerical integration, that goes back to a very big name in computational mechanics who worked with Zinkevich, and this is Bruce Irons. In fact, I would say Zinkevich was developing theoretical formulation, and Bruce Irons was developing numerical implementation. So luckily, these two together work nicely, and in Britain, you have a very clear structure of who is professor, who is collaborator. So there was lots of harmony in how they worked. Maybe not so much because at the end of his life, he left Britain because probably he would get sick and tired of Zinkevich, that he went to be a professor in Canada. It's very cold, so what the hell, you better go to cold rather than to Zinkevich. In any case, the idea is like, it is quite complicated for higher order approximation to obtain these integrals. Well, not overly complicated, but still complicated enough. And so the very good idea was not to compute them analytically, but to compute them numerically. And that's what I wanted to explain now for the remaining part. Namely, the idea goes as follows. Imagine now that first you're going to have this shape functions to compute, or any of these expressions. This is like shape function of its derivative, let's say this one. And then basically you want to say this computation goes from 1:1 to 1. So what you do, you replace this by a polynomial. And you say that this is an approximation. And you actually make sure that this polynomial has the same value as the function you're trying to integrate at certain number of points. And these points are called abscissas, or numerical integration. And then you simply write the result as the value of these of the function that you're using, polynomials, times the weights. And so again, the best integration rule goes under the name of Gauss. This is Gauss integration rule, where unknown values are both integration points, number of them, and abscissas, of course, and weights. Let me try to illustrate what I'm really talking about. So the idea goes as follows. Imagine this is my, this is the function I'm trying to integrate. So this is the -1 to +1, and this is xi equal to -1, this is xi equal to +1, and this is the kind of function I'm trying to integrate. So this here would be a true function. This is this integral from -1 to +1. It could be internal force vector, it could be external force vector, it could be difference matrix component, and so on and so forth. So what I do is basically I take a replacing polynomial. Let's say if I replace it by 2 points, I take a point here, and I take point, let's say, there, and I make sure that I replace now the true function by some kind of approximation that matches this function only at these 2 points. So instead of integrating this that goes up and down, I simply integrate this that goes underneath of this term. And I write result in a way that takes the value of this function at the points that are called abscissas. So these are my xi L. And I multiply this by the weighting function WL. So let me go back to equation so I can take this in a more abstract setting. So this was the function. There was a jagged going around the place. I replace it with the polynomial, which is smooth. And I take the value of this integral to be equal to weights times the value of this polynomial established at certain number of points. So basically here you have like to decide what these abscissas are and what is this weights. So imagine if you have like a single Gauss point. Basically, what you can do with single Gauss point, you have one unknown abscissa and one unknown weight. So the only thing you can take for approximating polynomial is some kind of linear function, g of xi, which is a function of c0, c1. In other words, you have something like this. You have a g of xi to be c0 plus c1 times xi. So let me go back to, again, sharing the screen. I can do this. This is precisely, imagine now this is the straight line. And well, let me go back to this one. This was this guy, this is that guy, oh. And this is this stuff that goes like that. And what I do is I simply take it there, oh, and I replace it by the straight line. And so this thing here, oops, this thing here is at xi. This is xi equal to 0. You know, and basically, well, I didn't really draw it correctly. Let me go back again. In fact, you know, the idea is like this was it. This was that guy, and And basically, this goes like that. So you can imagine that integral, which has this jagged edge, has been replaced where I take an approximating polynomial to be simply a linear polynomial, straight line. So if you want to obtain the value of this surface, because that's what integral is, this will be simply the value in this will be like this value plus that value divided by half, which is nothing but the value of this in the middle. So this is, g of, oops, this is g of 0. Not very successful, sorry. And this distance here, this is -1, and this here is +1. So the area, the +1, +1. And this guy should go way up. So basically the area of this guy is nothing but this guy times that. So this is times 2. So basically, if I go back to this one, I will simply obtain that the is equal to 0, and the weighting factor should be equal to 2. So you take the integral that I have to compute, I multiply by 2, and I have the
Hello, is connection alright, or is it only me?
Okay, do you hear me again? Is it okay?
Yes.